All right. So today we're going to talk about radian measure. Talk about sinusoids. Sinusoid is just the name of every kind of trig graph that we have. We're going to review all 6 trig graphs today. And then how to move those trig graphs side to side and up and down. So we'll be working on mostly graphs today. We're not going to work on the unit circle till tomorrow. All right. So it is assumed from this point forward that everything is radian. Okay? If they actually want you to use degrees, then they will have the little degree symbol. But if there's a 60 without the little degree symbol, the implication is it's 60 radians, not 60 degrees. Okay? If they have a 90, it's not going to be 90 degrees unless there's the little degree symbol. So from this point forward, everything should be, think radian. Okay, so what is a radian? Okay, the radian is the measure of the arc, or the amount. So it's like a ratio. It's the amount of, it's the fraction of the circle represented by the wedge. Okay, that is a radian. So 1 radian is not the same as 1 degree. Okay, because 1 degree is out of a total of how many? 360. So 1 out of 360 is very small. Okay, but 1 radian is out of a total of how many? 2 pi. And 1 out of 2 pi is 1 out of like 6.28-ish. So 1 out of 6.28 versus 1 out of 360, 2 very different things. Okay, that's why the units are going to be really important. I like to tell the story about the importance of units. My dad was a rocket scientist. He worked for NASA and retired just a few years ago. But one of his projects, he worked at the Jet Propulsion Laboratory, which is up in Pasadena. And one of his projects was working with a team from Colorado, and they had to kind of work collaboratively back and forth. One team was working entirely in the metric system, and the other team was working entirely in the standard unit system. And so everything like this big. So you're building this part and you're building that part, and let's go to put it all back together. And it was terrible. It was terrible. So yeah, your government dollars at work there, folks. So there we go. All right. A radian also can be measured using a right angle. That's where SOHCAHTOA comes into play. That measures with the unit circle. We'll talk more about that tomorrow. Okay. But what we just want to do right now is to practice some bare bones, like do you remember how to convert out of degrees into radians and back and forth? What? Okay. All right. So there's a quick little conversion. It's based on any relationship you want. So you've got, think of it this way, in the fractions of radians to degrees, there's a standard. Okay? That standard can be any equality that you know of that's true from radians to degrees. So do you have any memorized?
Like pi over 180?
Pi to 180. Those are equal. Okay? So that would work. You could use pi and 180 as your relationship. But it doesn't have to be pi over 180. That's the most common one that you learn, like in a pre-calc class. But you could also use 2 pi to 360, that would work because that's true. Those two things are 1. Okay, those are equal. You could do a half a pi to 90, whatever you want. Okay, so whatever you're most comfortable with. So pi to 180, and then you just cross multiply depending on the direction that you want to. So some people are like, wait, is it multiply by pi over 180? Is it multiply by 180 over pi? And which way do I go? And I just say don't worry about that. If you just cross multiply every time, the math will take care of itself. Okay, so let's suppose that we're converting 57 degrees. Okay, so when you want to convert 57 degrees, 57 would go in the position of D, which is in the denominator. So you'd have R over 57, and then being equal to pi over 180. And then you're just going to cross multiply that. All right, so we cross multiply. So we get 180R equals 57 pi. And so R is the fraction, 57 over 180 pi. Do not turn that into a decimal. Because as soon as you turn it into a decimal, you lose accuracy. This beautiful fraction, Okay, now you can reduce it for sure. Good.
Can you keep the pi in the numerator?
Sure, 57 pi over 180. Yep, either way is fine. Okay, is this reducible?
No.
Is there a number that goes into both 57 and 180? There is. 3. 3 for sure does. Okay, 3 does. Do you know how to check that, Christian?
3 you can add up on the digits together, and if it's multiple of 3, it's divisible.
Okay, so 5 and 7 add together makes 12. 12 divided by 3. And then 1 and 8 and 0 added together is 9. 9 is divisible by 3, so that means the whole thing is divisible by 3. So sure, if you divide 57 by 3, we get 19. If we divide 180 by 3, we get 60, and then pi. So you can write that as 19 pi over 60 or 19/60ths pi, either way. Now 19 is a prime number, so that's not reducible anymore. Okay. All right, so you can go the other direction. Okay, so convert 6/5 pi. Well, because it has the pi, the implication is that it is a radian. It also doesn't have the little symbol. Okay, so what if it had just said 6/5? Is that pi or radian?
Yeah, it is in radians.
Still radian. Okay, it's still radian. So you'd still put it in the numerator. Okay, only if you have the little symbol would that go into degrees. All right, so if we're converting 6/5 pi, so then we have 6/5 pi over d equals pi over 180, and then you cross multiply that way. So d times pi is 6/5 pi times 180, which is also reducible. Okay, it's reducible because the 5 can go into the 180. Okay, how many times does 5 go into 180? Well, 5 goes into 18. How many times? 3. Okay, with some left over. Okay, and so how much is left over then? 3, 5 goes into 30, we have 36. So you've got 6 times 36. Okay, so d times pi equals 216 pi. And then if you divide both sides by pi, the degrees then are 216, and now that is a degree. We put the symbol back on. Okay, any questions on conversion? Yeah.
Would we have our calculator?
Probably not. It would always be reducible.
So we have to do like 6 times 36.
And if you don't, there's always the old-fashioned multiplication. 6 times 6 is 6, carry the 3s.
18.
But it's also 6 cubed, which is helpful to know. 6 squared is 36. I just made this one up, so I'll try and keep the numbers small.
Wait, why would you not do like 6 pi over 5 times 180 over pi and then just multiply across? Like, is there a reason why you would do that? Or is that just a
6.
different way of doing it?
Yeah, just to, then,
Okay.
so I like to reduce first.
Seems shorter.
It's up to you.
Okay.
Yeah, you can for sure. So it's up to you. You're saying do 6 times 180 and then divide by 5 after that. That just makes the 6 times 180 for me, that makes it bigger. I'm not as good. I'd rather reduce the 5 in there to get my number smaller, because I can do 6 times 36 in my head, but can I do 6 times 880 in my head? And I got to think about, okay, I don't know. There's no, however your brain works best. Okay, let's go on to the graphs. Okay, we're going to review the 6 graphs, but it's really just 3 graphs. There comes in pairs of 2. So if you know sine, you should also know cosine. It just starts in a different place, but the shape is the same. If you know tangent, you should also know cotangent. It just starts in a different place. Same thing with secant and cosecant. So I'll show you some tricks. I did in your module, there's some trig graph paper. It's special graph paper to accommodate 2 revolutions of a sinusoidal graph. So please use that trig graph paper going forward, and I'll show you what that looks like. All right, so a sine graph and a cosine graph. You've got the key feature is where it starts. So sine starts on the origin and the cosine graph starts at a peak of 1. But other than that, the pattern is the same. You're just starting at a different point in the pattern. How do you keep that straight, one over the other? There's a couple different ways to think of this. One is the symmetry idea we talked about last week. This has even symmetry because the y-axis splits it right down the center. This one has odd symmetry because the origin is the point of symmetry. And so that's one way you can keep those straight. It also ties directly into the unit circle and what the values on the unit circle are. That 0, 0 and 0, 1 correspond to the values on the unit circle. That means at 0 radians, the sine value is also 0, sine being the y value along a graph. And then 0, 1 would be at 0 radians, the cosine value is 1. That's the x value along the graph. That's another way. Okay, you should be able to just sketch that. I usually look for 5 things when I'm having you sketch it. I look to see that those 3 dots are in the right place. Okay, does the beginning dot and the end dot, do they match each other in terms of height? Like is one up high and one, like they should, the beginning and the end should match. Is the middle dot in the middle, or is your thing, does it look, like this? Like, I don't even know if I could, like, I don't know, is it all like out of whack? I mean, it should look like the semblance of a sine graph. And then does it cross the x-axis where it should? It's not erasing. Okay, well, whatever. Are these dots in the right place? So it's 5 dots that I'm checking just to make sure they're generally in the right spot, and we'll go over how to get those. All right, tangent. Tangent also goes through the origin. So what kind of symmetry will it have? Odd, because it goes to the origin. So tangent is also an odd graph. Tangent has a bunch of things that sine and cosine don't, and are called the asymptotes. So a tangent is going to have all these asymptotes drawn on there. Okay, typically I'm looking for 2 asymptotes. So again, I'm looking for 5 things, and the 5 things would be these 5. 3 dots and 2 asymptotes adds up to 5. Okay, so 3 dots in the right place, 2 asymptotes in the right place. Those are the 5 things I'm looking for. And so the same, or it'd be similar when we move on to cotangent. I'm going to look for those 5 things. 3 dots, 2 asymptotes. With secant and cosecant, it's going to be 3 asymptotes and 2 dots instead. But there's always 5 things. Yeah?
So do you not have to do the asymptotes on like negative 3 pi over 2?
You don't have to. You can. I just, at a minimum, that's what I'm looking for. Okay? At a minimum. Okay, other questions on that? All right, so the difference in cotangent, which is where the asymptotes are. The asymptotes on cotangent go through the origin. So tangent so this no longer has odd symmetry because it doesn't have a point at the origin. So these would probably be the 3 I would be looking for, the 3 asymptotes, a negative pi, a 0, and a pi. And then the 2 dots I'd be looking for would be these. Okay, and the direction of cotangent is always a decreasing graph instead of tangent, which is like an increasing graph. Okay, if you did, so I'm looking for 2 cycles, two branches. If you do more, great, but you don't have to. Okay, that would be the minimum I'm looking for. Oh, let's just quick talk about symmetry here. Okay, it doesn't go through the origin, so we've established that it doesn't have odd symmetry. Does this have even symmetry? Okay, does the y-axis split it down the center? If you could take the y-axis and fold your paper right along the y-axis, would you get a mirror image? And the answer is no. In order for it to have even symmetry, the graph would have to look like this. Oops. It would come down like this and then go, that would be even because now you have the blue branch that would come down, and then the other would have to go back, like it would have to look backwards, but it doesn't do that. So this doesn't have any kind of symmetry at all. It's not even or odd. It's neither. Okay, I covered your question. Okay, great. All right. Okay, both of these have ranges that are all real numbers. Okay, the ranges are the lowest to the highest, and tangent and cotangent both go down to infinity and up to infinity, so they both have infinite ranges. They do not have infinite domains. Their domain is all real numbers except where the asymptotes are, so you got to know where the asymptotes are. Okay, let's back up. All right, secant and cosecant. All right. The way that I remember the difference between secant and cosecant is to remember which graph they are connected to. So secant is connected to cosine. I remember that because it's like SEC and then COS. I don't know. It's a consonant on the outsides with a vowel in the middle. I don't know. SEC and COS. My brain just somehow connects those. But a cosine graph should fit within your secant graph. Okay? So my cosine graph fits in here and then fits in here. Okay? So if you know where a cosine graph is supposed to fit, then a secant graph is just going to connect on the maximum and the minimums and then head out from those two directions. So I often will sketch a little baby cosine graph in mine, maybe erase it later, and then use this maximum peak to form my upper branch for my secant. And then I use the minimum value to form the branch on the bottom. And then I know where my asymptotes are going to go, because my asymptotes have to go every place that cosine crossed the x-axis. Okay? When cosine crosses the x-axis, what's its value? 0. Okay, so when cosine crossed the x-axis at pi halves and at negative pi halves, and then again at 3 pi halves, its value is 0. Okay, what's the reciprocal of 0?
0.
No. Okay, the reciprocal of 0 is 1 over 0, which is dividing by a 0 value, which gives you an undefined number. That's why there's an asymptote there, because it's undefined. Every time cosine is 0, you're going to have an asymptote. So the same thing would be true for sine. Every time sine is 0, that will make an asymptote there, or undefined.
If we have to make an asymptote, or if it's asking where the asymptotes are, would the one we have to write a formula with n, or would you just write the asymptotes of x cannot equal?
Okay. Great, good question. I'll accept either. Do you see how they're doing it like this? And they're just saying it's going to be at plus or minus pi halves, and it's going to be at plus or minus 3 pi halves, ... Okay, that means here I've shown you where the first couple are, the pattern follows for that. Okay, now if you were going to write it like that, you would be looking for, okay, my pattern is that there's a plus or minus. My pattern is that there's a 2 in the denominator. My pattern is that there's a pi in the numerator. That's all the same. And the pattern is, if I assume that there's a 1 here, and then the other one was a 3, and then what would the next pattern maybe be?
5.
A 5. So the next one would be a 5, and the next one would be a plus or minus 7, and the next one would be plus or minus 9. And so they write that with an n or a k. This is what you're talking about. They put a k there with the little note that k is odd. Okay, that would be one way, or n, if they use the letter n is odd. That would be, but you don't have to write it that way. This way, just with the little ... as long as you've given me 2 or 3, or this one in case 4 asymptotes, that's enough for me to know that you understand the frequency of how they're happening. Okay. All right, so sine is the one that fits in here. Hey, remember that sine started at the origin? And so sine looks like this and connects, and sine looks like that, and so sine fits right in there too. Okay, so they all have those moments of connection. They connect at the minimums and the maximums. Remember, sine isn't really there, but sine should fit within your drawing of cosecant. Now the range of that, there are two distinct ranges because there's a range for the upper half and a range for the lower half. And so you can see the range here is written. Part of this problem is always less than or equal to 1 with a range. The other one is greater than or equal to 1 with its range. And so you would write that it's got two separate distinct ranges, an upper range and a lower range. Okay, are there any questions about that? All right, so let's try this. Y'all also got to worry about how a graph is adjusted. What changes? So some things about the graph are always the same, the shape, but the labeling of the graph is going to change according to the numbers that are given to us. Okay, we can affect the amplitude of a graph. When you affect the amplitude, that's affecting the high-low. It's always the number in front. Okay. You can affect the period of a graph, and we calculate that using 2 pi, which is a full circle, divided by the value of b. So it's always 2 pi divided by b to figure out your period. Our vertical and horizontal shifts are exactly the same as they were before. If they were inside a set of parentheses, they're going to move things side to side. And if they're outside the set of parentheses, they're going to move it up and down. We can also reflect this. How do you cause a reflection to happen?
Negative.
A negative. Where would the negative need to be?
On the outside of the F.
Okay, so it depends, and f could be anything, right? F is a function, so this f here could be sine, it could be cosine, it could be tangent, it could be secant, cosecant, or cotangent. So that f is just meaning any trig function. But yeah, if you want to affect a reflection, you would have to have it actually in front of the a value. And that would reflect over the x-axis because it's outside. So that would reflect over the x-axis. If you wanted to force a reflection over the y-axis, then your negative would need to be inside of the parentheses, but it would need to be in front of the b. So it's either in front of the a or it's in front of the b. And that negative, if you force it in there, would reflect over the y.
So it's the opposite of the shifts. The negatives.
Yeah. Okay, so let's take a look at this. Determine what the period is going to be, what the domain, the range, and draw the graph of this following function. All right, so we want to analyze this and what's all going on here. All right, so let's take a look at this. What does that tell me?
Reflect over the x.
Okay, that is reflecting over the x. Okay, what about the number 2? That is the amplitude. Now, a common misconception is for people to say that the amplitude is -2. The amplitude is not -2. The negative is the reflection part. The amplitude is the value of 2 because this graph will have its highest point at 2. Okay, that is the amplitude. Yeah.
The amplitude always has to be the absolute value, right? So it can never be negative.
The amplitude is never negative. It's always the value of the highest point. So even though this will go up to 2 and down to -2, the amplitude is said to be the absolute value of that, so 2. All right, what about this number 4 here?
Is that a stretch? It goes up to 4?
No, you're thinking this way, which is an amplitude. Okay, Chloe?
You like take it out and it's the like.
Oh, that's right.
And
You
then
pull it out
and this pi over 4, and you take it out and that's it.
Okay, yeah, so we are going to factor it out. We're getting there. Yeah, the number 4 tells us how many cycle waves we have to squeeze into the 2 pi space that we have. We have 2 pi space to work with. So we're going to squeeze 4 of them in there. 4 cycles. So how big is every cycle? If you have to squeeze 4 cycles into a 2 pi space,
It's 2.
okay, so that's where the period formula comes from. 2 pi over 4. Okay, it's 2 pi divided by b. So that turns out to be pi over 2. So every cycle is pi over 2 in length. Okay, completes its cycle in pi over 2. All right, then Chloe was also saying, yeah, don't you have to like pull it out and, okay? The answer is yes. Yeah, go ahead, Ed.
No, I'm just thinking out loud.
That's okay. Do you want to process out loud, or are you still just gonna?
No, I'm just thinking.
Okay. All right. So we have this plus pi. What direction? To the left. How much? Okay, not pi, but pi over 4. So this is where Chloe was talking about that. All right. So if you had 4x plus 8, and we said pull out the 4, okay, that becomes 4 times x plus 2. Okay, how do you get the 2? Divide 8 by 4. Okay, it's division. All right, so if we have 4x minus 64, and we say pull out the 4, then it's 4 and x times, or x minus, and then what do we get? 16. Why? That's 64 divided by 4. So the same is true in trig. We say pull out the 4. That's 4x plus, and then the process is division. And so it would be pi fourths is what is left with. Now, how can you check your work? Distribute it back in. Okay, distribute it back. And you should end up with the thing that you started with, which was 4x plus pi. So we really need to think of this problem differently. We need to insert another set of parentheses in there. And erasing just doesn't like it, okay? And then we'll divide that by 4. And so our shift is going to be left a value of pi fourths. All right, now, I love Notability doing most of the work for me. So on the next slide, we're gonna actually graph this. All right, remember I said I was gonna grade 5 dots. Okay, here's my 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. I like to space mine out 8. You can do 4s, you can do 2s, whatever. Just make them even, equally spaced. And then there and there. Okay, there's my sine. Those are the bones. That's the skeleton of my sine graph. Okay, 5 things. Okay. I haven't done this in several months. Okay, I'm a lot of practice, a little wobbly. All right, there's my sine graph. 1 cycle to start is fine. We can add more cycles later, but I just like to start with 1. Okay, I always draw first and label second. Some of you like to label first and draw second. I feel like that's harder. Draw first, make your drawing. Get nice and spaced out so you've got your space. Okay, and then some people go, yeah, but I thought we had to cram it in and like get it to be, yeah, this is gonna have a period of, what did we say the period had to be? Okay, well then label your period as pi over 2. There, my period's pi over 2. I didn't have to like squeeze it into a little crammed space. I just made that spot pi over 2. Okay, I can control that. Which then makes what in the middle? Pi over 4. Okay, which makes this pi over 8. And if you multiply that by 3, you always get this one. So 3 pi over 8. Okay, that again, that's the skeletons, that's the bare bones. We want the amplitude to be 2, so we'll label 2 and negative 2. We want to reflect this because it was supposed to be reflected over the x-axis. So then we will reflect it. And then we need to slide it to the left, pi fourths. Okay, so I'm gonna grab, oh, I'm not in Notability, okay. I can't grab because I'm not a Notability, but I'm going to move this whole thing pi fourths. And how many tick marks represent pi fourths on my graph? 8. So I need to move this whole thing over 8 tick marks to the left. Okay, and moving it over 8 tick marks to the left is going to end me up like this. And lo and behold, I end up right on the same spot that I was my original black graph. Okay, and that's the graph. Domain for sine and cosine is always all real numbers because they don't have any asymptotes. The range for this one, the lowest value is -2, and the highest value, the amplitude, is 2. So that's my range. Okay, any questions on that? Okay. Cosine, I'm going to do the same way, but I'm going to start differently. The bones of a cosine graph are going to start like this. Here's my bones, 4 and 5. Okay, 5 dots forming the bones of your graph. And then move it as you want and label it as you want. I'll put one example of a tangent graph on the video so that you could watch a tangent option as well, okay? All right, one thing I just want to throw out here before we start talking about the unit circle is just a little bit of number sense here. If I give you these two numbers and I ask you to put an inequality in between them, which one is bigger? Which one is bigger? The rad 3, okay? How many of you think the rad 3 over 2 is bigger? Okay, how many of you think the 1/2 is bigger? How many of you are unsure how to tell and are unwilling to commit one way or the other? All right, so the denominators are the same, okay? So we can agree that the denominators are the same. If I do this, does that change anything?
No.
Why?
Because
Square root of 1 is still 1. Okay, so the denominators are equal, but the numerators are different. So which numerator is bigger?
Rad 3.
Rad 3 is bigger than rad 1. Therefore, this is bigger. Okay, that helps me on my unit circle keep track. Now when I'm looking at my unit circle, and I've got these rad 3s over 2s and 1s over 2s, like which one comes first and which one comes second, it helps to know which one's the bigger one. Okay, rad 3 over 2 is bigger than half, and it's the x-coordinate. And so in that position, the x-coordinate is bigger. You just have to look at the measurements. If I measure the x this way, and I measure the y, clearly the x, which is the cosine value, is larger than the y, which is the sine value, so that helps me out. Okay, the rad 2s over 2s, I mean, those are equal, so you can't hardly ever get those wrong. All right, but then you've got it here. Now the bigger one is the y value. And so if you think of that in terms of putting a triangle in, now you have a bigger height than the base. The base is smaller and the height is bigger, so that means your y value has to be bigger. So that helps me think about which one is which in terms of my x and my y. How do you remember that cosine's the x and sine's the y? Does anybody have a trick?
The C comes first.
C comes before S in the alphabet? Like alphabetically, cosine has to come first, okay? So that works, I don't know. Okay, okay, now you're good. I have only ever memorized quadrant 1 because I can figure out all the other quadrants based on if I know quadrant 1. And so I just, in my head, I go, okay, quadrant 1, flip it over, and then I can do it that way. All right. So that's just there for your reference. Okay, what is going to be more important? I mean, yes, you're going to have to know, like, what's the cosine of pi thirds? And you'll need to be able to come up with that. Okay, what's the tangent of certain values? You'll need to be able to come up with that. Tangent is going to be sine over cosine, so y over x. All right, but what is going to be more important as we move forward in calculus is that you know how to do the inverses, which is working backwards. The answer to an inverse is always going to be a pi value that goes with it. Okay, it's going to produce the pi value that holds that position. So sine of 1/2 is looking for a y value that's living somewhere on the unit circle that has a value of negative 1/2. So there are two places where the y value is negative 1/2. One is here and one is here. Okay? Because of the rules of inverse functions, let's think about last week. What does an inverse function need to do? What does it have to pass? Horizontal and vertical line test. Okay, because of that, we never can use quadrant 3, because quadrant 3 would cause us to fail the horizontal line test. So you will never have an inverse answer that's coming out of quadrant 3. So that helps you eliminate half of your answers, a quarter of your answers. But in this case, the two I have to choose from, 50% of it I can eliminate. So the only answer I've got is the one that's associated right here. Now this is associated with the radian measure, 11 pi sixths. However, in inverse trig, 11 pi 6 is a forbidden value, because what does it take me to get to 11 pi 6? If I were to send me on a route starting at 0, what direction does a unit circle go? Counterclockwise. And if I go around this circle, what have I just entered? Which quadrant? I just entered quadrant 3, and we're not allowed to go into quadrant 3. So how can we get to that value without having to go that way? We go negative. Okay, so the answer to this can't be in quadrant 3, can't even take us through quadrant 3. The answer is negative 1/6 pi, or negative pi sixths. Yeah?
Can you go through why we can't go into the form of 3 again?
Yes. So it goes back to the sinusoidal shape of the graph. Okay? So all sinusoidal shapes, so you've got that sinusoidal shape, which is cosine and sine, just shifted. And then you've got the sinusoidal shape of tangent, and then there's another one that repeats. If you line up the quadrants with your number line, okay, so quadrant 3 is from pi to 3 pi over 2. If you go to that same section on your number line, okay, so that would be this section, it's going to fail the horizontal line test. And if I go to that same section here, it's actually up higher, it will fail the horizontal line test. So we exclude, because of we need the horizontal line test to pass. So we limit ourselves to only quadrants 1, 2, and 4. And 4, you can only get to 4 by going backwards. Okay? All right. All right, so then we're looking for a cosine inverse of negative rad 2 over 2. Again, there's a couple of those. Okay, if I'm looking here, cosine inverse would be an x value. That was negative rad 2 over 2. So I can see an x value here. I also see an x value there. Okay, my 50-50 rule says eliminate anything in quadrant 3. And so associate your answer with quadrant 2, which you can get to in a forwards direction. And so the answer to that would be 3 pi fourths. Okay, any questions about inverses and those rules? Okay. All right, the other inverses we're going to deal with triangles. Okay, because 4 and 9, how do you know it's unit circle and not triangles? Well, it doesn't have square roots in it. And it's not a rad 3 or a rad 2 or a 1. Okay, so anything, it's going to be a triangle otherwise. If it's not a nice unit circle number, it's going to be a triangle. So we solve this by sketching. I like to solve it by sketching a SOHCAHTOA triangle. It doesn't matter where you put theta. Wow, I didn't really like how that turned out. Try that again. Theta can go in any corner. It can go in the lower corner or the upper corner. So those are called angles of elevation or angles of depression, doesn't matter. Okay, we know we have opposite here. We know we have adjacent. And we know we have the hypotenuse. If we are working with the fraction 4 over 9, which is part of the sine value, sine is SOH, S-O-H. And so this is O, which stands for opposite. This is H, which stands for hypotenuse. So my opposite right now is 4. My hypotenuse is 9. So if I do, what kind of formula to help me figure out? Pythagorean theorem, because it's a right triangle. So a squared plus b squared has to equal c squared. So 4 squared plus the base squared is going to have to equal 9 squared. That's 16 plus b squared equals 81. So b squared, or b itself, must be what square root?
81 minus 16.
Which is 65. All right, so my base, my adjacent, is rad 65. So now the question is, tell me all 6. All 6 trig values. So the first 3 are sine, cosine, and tangent. Okay, after sine, you need to put theta. Yeah.
So like how would the first thing be different if sine wasn't an inverse?
Okay, that's a whole, yeah, that is a whole different ballgame. If sine was not an inverse, then 4/9 would represent the value of the theta in here and not the value of the sides. Okay, when it's an inverse, we're looking at the value of the sides. When it's not, we're looking at the value of the angle. Okay. Because in a right triangle, we don't have negative sides. All right, so sine, cosine, and tangent. So sine, we already know, is going to be 4/9, which means CSC is going to be 9/4. So those are paired up. One is the reciprocal of the other. Cosine is rad 65/9, which means secant is 9 over rad 65. And no, you do not have to rationalize anything. You can leave your fractions just as they are. And then tangent is TOA. So opposite over adjacent, and the rad 65 is in the bottom, totally okay. And then cotangent would be rad 65 over 4. All right, I was going to do one more with you. What is the tangent of the inverse cosine of 3/7? All right, still a right triangle problem. The 3, because this is cosine, which is so ka-toa, then my adjacent is 3 and my hypotenuse is 7, which means my opposite is going to be Pythagorean theorem, square root of 40. All right, and then all I have to do is find the tangent. I don't have to find all 6. This is specifying one of them. So all I have to do is then the tangent of that value is rad 40 over 3. That's it. Okay?